Okay, so we're going to take a look at aberrations. This is sort of an addition to our section 2.4. And aberrations are basically the case where we get an imperfect focus, and this leads to a blurry image. The two most common are spherical aberration and chromatic aberration. Now, going forward, spherical aberration happens because it's very easy to grind a spherical surface on a lens, much more difficult to grind a hyperbolic surface, which would have been the preferred way of doing it. But with the spherical surface, it tends to be too curved at the outer edges and tends to be not curved enough in the center. So the outer edges actually have a stronger focusing power and therefore a shorter focal length. And this results, of course, in a focus which is blurry, or basically an image which is blurry because there's not one place that the light will focus to a crisp image. For lenses, the way to get around this, or one of the solutions to this, would be to create a hyperbolic surface as opposed to a spherical surface. Now, we talked about the fact that we're not curved enough at the center and too curved at the edges. And again, this leads to this uneven focusing along the optical axis. Too short from the rays on the outside, too long from the rays toward the center of the optic axis. Now, if you remember your hyperbola, it's basically less curved on the outer edges where a sphere has a constant curvature. So this creates a better focus, again, at the center. You're focusing at the same point as on the outer edge. And really, you can think about the hyperbola. It flattens out. It reaches basically zero curvature as it approaches its asymptotes. So if you could grind a hyperbolic lens easily, there would only be hyperbolic lenses. But again, spherical lenses are a much easier type of shape to grind on these surfaces. The other way that you could get around this, and this is even more difficult, but with the advent of more sophisticated materials, we can actually take a trick from our own eye. The lens in our eye actually has a greater index of refraction at the center than it does at the edges. And if we had what's called a gradient index lens, meaning that your index is highest at the center and less at the end, you would delay the wave front most at the center, allow the outer edges to catch up with it. And again, if you have the profile just right, you can get a fairly sharp focus. And again, that's something that nature has been able to do that we don't have as easy of a time doing. We do see some of these gradient type index profiles in optical fibers, but again, if you think about the way most glass is made, we're actually casting glass from a molten material. So to get the center at a higher index than the outer edges means that you would have to play some pretty neat tricks that I'm not too familiar with. I think a lot of it has to be about doping the center with things like higher index materials such as rutile. Chromatic aberration, basically going back to what we had with a prism, the index of refraction for violet light is going to be higher than that for red light. And we saw with the lensmaker equation, the focal length depends on the radius of curvature of the surfaces, but also the index of refraction. So violet light will experience a shorter focal length than red light. You can clearly see the violet light is focusing closer to the lens than the red light in this diagram right here. Again, anytime that you don't have everything focusing to the same point, you lose the crispness in your image. Basically, you don't have a well-focused image. And here's a very good example of what you tend to see. You tend to see these chromatic edges on the images. And here on this weather vane, you can see one edge is sort of has this reddish, the other edge sort of has this bluish edge to it. And again, that's really because the light is focusing at different places or different distances. Now, again, we need to come up with a solution of correcting for this. And one of the ways to do this is to use multiple lenses. And there's something called an Apochromat, A meaning lack of, chromat talking about chromatic aberration. We use two lenses in what's called a doublet. And one lens is made out of a higher index material, and the other lens is made out of a lower index. And what this does is you have to be very careful with the way that you design this, in that the chromatic aberration from the biconvex lens has to be canceled out or nearly canceled out by the meniscus lens here. Here you can see, here we have our biconvex, right? And then here we have our meniscus. And again, the chromatic aberration you have from the first lens has to be canceled out by the second lens. And that takes a bit of engineering. It doesn't just happen naturally. It has to be well calculated such that you move the red and the blue focuses overlapping one another. You still have some chromatic aberration. You actually have the green light focused at a slightly different place. But that difference that you see here with the achromat compared to the just single uncorrected lens, you have a greatly improved image right here. And you can see that your image size or your spot size is about 1/30th that of the chromatic aberration image. So using multiple lenses is one way of getting around this. It's more expensive, obviously, because you have twice as many lenses. It can be also quite challenging because each lens has to be designed to complement one another when creating these achromats. And again, you can see here, here's our range of different image distances for the achromat, where for our uncorrected lens, a simple lens, a single lens, there's a huge range, and that certainly would create that unwanted blurring that you see with the colors in this image. There are other problems with that image too. That has a lot of distortion, that particular lens, but it's using a very, very short focal length lens, and the shorter the focal length, this is very key, the more problems that you generally have with producing an image. You get more distortions. Now, there's actually something called an apochromat, and in this case, we use 3 lenses, and the idea here is to bring the red and the violet light together at the same time bringing the green. So it's not as simple as saying the first 2 lenses bring together the red and the blue, and then the third lens brings the green, the red, and the blue together. It's really a combination of all 3 lenses working together. And as challenging as the achromat is to make, this, of course, would be even more challenging, much higher cost. And again, you can see here the small error created by, the small error created by the achromat, which has been blown up tremendously here, and then the apochromat has a even smaller error in it. So depending on how critical it is to eliminate chromatic aberration, you can design a lens system that gets rid of most or as much as you need to get rid of it. Just as a matter of how much you want to spend in creating these multiple lens systems. Now, spherical aberration also distorts the image. Here you can see a image created without spherical aberration, and one with spherical aberration. If you try to focus it, it never seems to come to a nice crisp focus, because again, the outer rays are focusing at a shorter distance than the inner rays, and you can't find a happy position. Either you're focusing the outer rays or you're focusing the inner rays. And that was a problem that the Hubble Space Telescope actually faced. They ground the mirror incorrectly. It is a computer-controlled grinding system that ground the Hubble Space Telescope mirror. Same sort of situation for the Webb Space Telescope, but they didn't have a problem with that one. And they're in such a rush to put the telescope in orbit that they never tested to see that the mirror was the right shape. And once it was in orbit, it was too late. What they were able to do, and this was really genius, they were able to introduce what are effectively eyeglasses to correct for the spherical aberration. And, just as someone might wear glasses to correct for astigmatism, I'm nearsighted, so these are correcting for my nearsightedness. Soon I'm going to need bifocals. Astigmatism is different in terms of one axis is focused different from the other axis. Again, this was the case of it wasn't spherically ground, but it wasn't the correct shape. So it was somewhere in between the desired parabola and a spherical shape. And they came up with an ingenious way of correcting this. And in fact, they had to use these correcting lenses for all the equipment. But it saved a multi-billion-dollar space telescope. And the rest is history. Hubble has been a remarkable machine. Coma is another type of aberration. What is the best way to describe coma? Usually when you have a short focal length, you will see an image that suffers from coma be very, very good toward the center. But then as you get further and further away, you start experiencing this blurring type effect, which is essentially because when you have a very strong optical system, a very short focal length, you're trying to project that onto a flat surface, such as a photographic plate or a detector. The distances from the outer parts of the lens or mirror compared to what's at the center become problematic. So you get sort of this spreading out, or this coma, where it may be again in focus for the inner rays, but not the outer rays. And again, this typically happens when you have a very short focal length. And why would you make it a short focal length? Because that's where you get a system that acts as a very nice light bucket. It concentrates the light very well with a short focal length if you're using a telescope. So again, we can see how this happens. We're creating this coma-like shape from the rays coming from the center compared to the outside. And you can see how, again, for a short focal length, we get this blurring effect. And the way to create less coma is to use a properly shaped mirror. A parabolic mirror does eliminate some of the coma. A hyperbolic shaped lens also reduces some of the coma. But you do have a little bit of field curvature too, which can be a problem even with the proper shape here. Hyperbolic mirrors, we got to be careful with how they are used. It's not really completely correct that a hyperbolic mirror would be superior to a parabolic mirror in all cases. A hyperbolic mirror is good for focusing a point source to another point source. So sometimes they are used in combination with other mirrors and help eliminate some of the aberrations that you might experience. I talked about astigmatisms before. Now, if you go to an eye doctor, the two most common errors that you'll have for your eye, when you get older, you've got other problems, but the two most common errors you'll have with your eye in terms of the curvature of the cornea is it's not shaped the right way, so it focuses either too much or too little, or in its axis, and this is very exaggerated, it'll have a shorter focal length in one direction, say the horizontal, than it'll do in the vertical. And obviously, this creates some of the same problems that we had with spherical aberration. You'll never be able to focus the light completely. And the way to correct for this is to come in with some type of lens which is slightly elliptical rather than spherical. And by elliptical, I mean that it focuses stronger along one axis than the other axis. And again, you can see how we can run into some of these problems where focusing at different lengths. This is a little bit different because this is sort of an off-axis type aberration that occurs. But again, the complexity of designing a high-quality optical system can't be understated. It's really, really easy just to grind a spherical lens and a spherical mirror and get a simple telescope or microscope that could be sold cheaply. To really get perfect images or nearly perfect images or images that lack aberration requires oftentimes very unique shapes or even multiple elements. And again, these are just some of, I don't even know the names of these. These are actually eyepiece designs that are being used to correct for chromatic aberration and correct for spherical aberration and some other problems. You have to balance everything at once. You can't just design a lens and say, I'm going to correct for chromatic aberration, and then tweak it and say, well, now I'm going to correct for spherical aberration. Everything has to be done at once. And that creates a real challenge for optical engineers. Look at this cutaway of a camera lens. And when we're taking a picture of something, a really high quality photograph requires a nearly perfect image to form on whatever medium that we're focusing it on. Maybe it's film, maybe it's a CCD, but we want as perfect of an image as possible. And in this camera lens, I may be wrong, it might be slightly telephoto too. We need, how many lenses do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 different lenses. They all have to be ground to the exact shape, polished. And they also have to be coated. We'll talk about anti-reflection coatings later on. So you go camera shopping or camera lens shopping, and I'm always shocked by the price on some of these lenses. A really professional telephoto lens is going to be over $1,000. And again, the sticker price is shocking until you realize that the optical elements inside, you're paying for not only a very well-designed piece of equipment, but high quality elements inside them, multi-coated lenses, precision mounts that are not going to allow the lens to get out of alignment. Quality equals larger number of elements, and as it says here, more price.